Hi everybody, welcome back to Chemistry 131. You'll notice that on the bottom there, in the announcement box for me, there was a date change because I put the wrong date for the lab yesterday. I mixed up which class was what and was just visualizing the chart in my head and thought the middle block was Wednesday for the syllabus. So I changed the date so that it matches with the syllabus, which means that it's actually due one day earlier than we mentioned yesterday during the lab. So just be mindful of that. The date's been updated. You should get an email that says assignment date changed. And that's really the only announcement so far. That's also the only thing that's due so far. So make sure that you are working on that when you get an opportunity, and don't wait till the last second because making those models may take a little longer than anticipated. So the first quiz, I've already written it. It will go up when we finish chapter 12, which will hopefully be Wednesday. There's quite a bit of content left to cover, but some of these sections, like for example 12.6 here, is a very short section. And a lot of the things that we do in 12.4 and 12.5 are going to come up again in 12.9. So once we know how to name stuff, which we're going to do in the first hour, this will go a lot faster. So the first thing we want to talk about is we want to talk about different ways to draw Lewis structures, because there are a ton of different methods and they all convey different information, and some of them are just simply more convenient. Now, on the right here, I have drawn the Lewis structure, which for our purposes in this class, we're just going to call the structural formula. This is the structural formula of C5H12. It is the Lewis structure where each carbon has 4 bonds coming out of it to fulfill its octet. Hydrogen, if you recall, only needs 2 electrons, so it only needs to make 1 bond. By arranging my C's and my H's in this manner, I am able to fulfill everybody's octet or duet in the case of hydrogen. Now, I could have rearranged the carbon bonds and made a branched alkane, but for the purposes of our example, this Lewis structure is correct and satisfies this formula. What we're going to then do is we're going to take each of these highlighted groups here. So I'm just going to put the yellow highlighter over these. I'm going to condense those down. Instead of drawing them out like that, I'm just going to write what those are. So the red group I would call CH2, and the blue group I would call CH2, and the green group I would call CH2. And then the black bookends on both sides of the molecule I would call CH3. I could write that as just a sentence sort of formula, which we're going to call a condensed condensed structural formula. And so all I've done is taken away the bonds and condensed down everything into sort of vertical slices. So I'm making vertical cuts along the molecule and then just writing what I see. My branches are always going to go up and down in this case. In condensed, they have to be in the order that the molecule shows you. And we're going to do a few examples, and then I'm going to show you even more examples because the text doesn't really go into enough detail. But the gist of this is going to be that you're going to just write the first carbon that's furthest to the left, so we'll say leftmost, and then what it's attached to. And then repeat that. So this is the next carbon and what it's attached to. And this is the next carbon and what it's attached to. And this is the next carbon and what it's attached to. And so on. Now, if you have branches for atoms that are not hydrogen, then this gets a little more complicated. For the most part, you just simply write them in. So if I had this molecule instead, Let me do this. That's the wrong button. There we go. Oops. So we'll put this up at the top here. I actually need to open Chemdraw really quickly, so let me get Chemdraw. Hopefully I won't make it beep at me, because it's really loud if I do that. So let's see here. So I'm going to make a molecule really quickly. Unfortunately, it takes me a second to do this in Chemdraw if I draw out all the bonds. And you're going to see what our solution to that is going to be later. Let's just stick a bromine in here too. So I got to go hydrogen, 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 hydrogen. Okay. So hopefully I can copy this, and then when I go in here, oh, I got to zoom in real fast. And then I hit paste. Okay, it did copy. For some reason, nothing happened. There we go. Okay, so here's my molecule. Let's suppose that... I don't know why. Oh, I don't have it selected. Okay. Let's suppose that I wanted to write the condensed structural formula for this molecule. And so what I would do is I would make vertical slices again. And I'm really zoomed in, so my pen's going to be kind of low resolution here. But I would then say, okay, the first one's CH3. And then the next one is CHBr. I'm going to do the H before the Br. And the reason that we're going to do the H first is because it's really small. We're going to put the smallest thing first when we're listing off other things that are attached here. And then this would be CH2. This would be CHCl. And then finally, this would be CH3. So if you see other groups, and those other groups are just one atom, just list them. Now, if this was instead maybe another Br, then instead of this H here, we would just do Br2. And that's fine. Now, what happens if we have something like this? So instead of H, we had CH3. Then we have to do something different. We're going to show that on a slide coming up. I got to zoom this canvas back out here. Okay. So, for instance, let's look at this molecule here. What do I do in this circumstance when my vertical slice includes a methyl group? In this case, what we're going to do, so we'll again make our vertical slices here. Excuse me. And then we'll label it left to right, just like before. CH3, CH2, CH, and then I have a methyl coming off of it. So what I'm going to do is this. I'm going to put parentheses around it, and then include what the branch is. Now, if this is a bigger branch, like if it was CH2, CH3, I would write that instead. And then the green branch is CH2, so it's this one right here. And then this one is CH3, and then all I do is just put them in order. So I go CH3, CH2, CH parentheses CH3, CH2, CH3, which I have written below. Oops, that's the wrong arrow key. Which I have written down below here. Okay. Now, I've given you some very simple examples, and I have conveniently lined them up left to right for you. In reality, you're not going to have molecules that are this simple. So when you make your vertical slices, you're going to have to unravel your molecule and have it drawn left to right. Okay? Your vertical slices should always go through the bonds. All right, so let's do some more examples. Let's go backwards now. So now instead of drawing or writing out the structural formula, the condensed structural formula from a diagram, let's turn this into a structural formula. So I've written this down, and remember, each of these times we hit a C is a vertical slice. So make your vertical slices in the molecule, and then try and draw the molecule from those slices that you've made, and then bond all of those slices together. So I'm going to give you about 2 minutes to do this, and then we'll go over the answer together in just a second. So give it a try. Now, I realize that I can't actually see your answer when you do this. This is for your practice, but let's try and draw this out. So we're drawing the structural formula, so we're going to expand everything as much as we can. Actually, let's go to the previewer for this. There we go. And then we'll just get rid of this guy. All right, so I got CH3, so I'm going to draw that over here. And I got CH2. And we'll bond that to the previous one. Then I got just regular old C, so I'll write that. And that C is connected to a CH3 and another CH3, because there's two of them there. So we'll do that. And we'll do that. Now, if you wanted to, you could just write this. This could be implied, right? Sure. We'll bond that to the previous group. So this is the most complete way to do it up at the top here. But down at the bottom, this is a little more shorthand. And that's fine, right? We're not going to be that picky. Then I got CH, CH3. So we'll write that in there. We'll connect to the previous group. I already did that on accident. We got CH2. Connect to the previous group. And then CH3. Which means we must be done. There you go. You're always going to end with something with 3 attached to it. Now, they don't have to all be hydrogen. I could have CH2Cl. That's 3 things, so that'll be a capstone. Because we need to be able to terminate our chain with an atom that isn't C, so that we have our octet. So there would be our molecule, and let's compare that to the structure that I got, which is over here. And those look pretty similar. And you'll notice that I just simplified them as CH3 in this diagram, but you don't have to. You could draw the whole thing out. The reason that I did that is because I think I had to, like, drag the C to be higher or something like that. And when I did that in Chemdraw, it looked really, really goofy, especially since I had a second one next to it. So you can put it on either side, it doesn't matter. Now, for our purposes in this class, in this chapter, it doesn't matter. In reality, depending on where you do that, it may or may not matter. We're going to talk about chirality when we get to sugars in chapter 16 in carbohydrates. But for now, we're going to assume that, like, oh, you can just put things wherever you want to. Connectivity doesn't matter. And that's fine. If you look these up online, you might actually see something called stereoisomers. Don't worry about that yet. For our purposes, just assume that there are 4 directions. You could put them in whichever direction you want. All right. I have taken this molecule and I have turned it into a, like, bendy mess, we'll call it. And so what I want you to do is write the structural formula for it based on what you see here. Now, remember that when you're making vertical slices, you have to kind of elongate the molecule. You can either do that mentally or you could redraw it. I'm going to leave your strategy up to you and give you about a minute or so to do this, and then I will show you what I do. Okay, so give it a try. All right, so hopefully you have the answer by now. I need to draw on the structure, so we're going to do this on this page. So here's what I do when I do this type of structure. So I'm going to number my carbons 1, 2, 3, 4, 5 along the longest chain. Now, if you numbered this one down here as 5, that's okay. They're both equivalent. You can go either direction. And then what I'm going to do is I'm going to make my vertical slices. I'm going to just change them into regular slices. I'm going to just slice between the carbons. So they don't have to be vertical anymore. They can go whatever direction they want to. Now that I've segmented my molecule into its slices, we can then write what we see here. So let's do that. So carbon number 1 is CH3. Carbon number 2 would be CH bonded to CH3. So I will write CH, CH3, putting my CH3 in parentheses. Then carbon number 3 is CH2. Carbon number 4 is CH3. Uh-oh, I'm going to run out of space here. And then the last carbon 5 is CH3. We'll just go like that. That's good enough, right? And there you go. So this should match up with what we got. So we got CH3, CH3, CH2, CH3, CH3. Looks like it all checks out. So that's how you do this. I'm going to give you a few more of these examples to practice with later on. The next strategy that we're going to discuss in representing molecules is called the line angle formula. Oops, hold on, let's see here. Can you also write it as CH32? There we go. I gotta go back. There we go. That's what I want. So you can't do it as written like that because you would need to put the CH first. And also the problem with that formula here that you've written is that it doesn't start with an end group. You've started with one of the side chain groups. So the proper way to do that would be to say, okay, I would start with this and I would write this instead. ... But the problem there is that you aren't representing the longest chain. And so we need to include all of the carbons in the longest chain here. So don't abbreviate it too much, is what I'm saying. Now, for the most part, the abbreviated method is just kind of a formality, like, oh, you might see it written like this every so often. The main way that you are going to see structures written in this class is going to be for the line angle formula method. Okay, so here's our favorite C5H12 that we had before. And what I'm going to do is I'm going to simplify it. And first I'm going to show you the simplification. Boop, there you go. And then I'm going to explain what we did here. Now, you might be looking at that and going, wow, that really is simple. That's so simple I don't understand. And I can't criticize you for that because there's a lot of abbreviation going on in this diagram. Also, it's really easy to draw this. This would take me like 45 seconds to draw. This takes me 2. So we're going to be using this method all the time. And here's what it means. This is what we did. So the first thing that we're going to do is indicate vertices or points on each zigzag. So let me get a color that isn't blue here. So this carbon right here is this point right here. I have 5 of those. So I'm going to have 5 either endpoints or points. And now that I've written through all those, I might as well do that, right? Then the next thing I'm going to do is I'm going to say, okay, all of these H's, H is sort of our fill-in atom, right? Whenever we need an octet, we can count on H to do that. And so what we would say is that H's are implied. What that means is that if I don't have an octet around an atom based on what I have drawn and shown, the remaining bonds that are not drawn must be H. So for instance, this carbon right here only has 1 bond coming out of it. So there are 3 H's coming out of it too. On the other side here, I have 1 bond coming out of this carbon, so the other 3 must be H's as well. What about the ones in the middle? How many bonds are coming out of them? And then how many H's must be coming out of them to fill in the octet? And hopefully you're shouting at your computer screen right now, it's 2! Because it is, because I have 2 bonds for each carbon, and then the other 2 must be H. And then in this case down here, same thing, and then same thing. So I've taken my molecule and I've drawn all over it, and I've made it really, really, really messy. But what the H's being implied does for us is it makes our structure way simpler, because 90% of your time drawing these structures, you're drawing H's. So that's how we're going to decipher line angle formulas. We're going to draw a point for each carbon, connect all the points with bonds, and then anything that's bonded to an H we omit. We're going to assume the missing atoms in our structure are hydrogen. That's not a very good answer example because the answer just appeared. Here, draw this line structure. Oh, there it is. Hold on. So pretend you didn't see that. We'll just cover it up. My animation didn't cue correctly. I didn't tell it to do that. That's okay. All right. We're going to draw this line angle structure for this molecule. So the first thing we want to do is we want to count the carbons in the chain. So if this up here is my structure, then I've got CH3, which would be the first carbon, and then the CH3 would be the second, CH2 would be the third, CH2 would be the fourth, and then CH3 would be the fifth. So I should have a 5-carbon chain, so I'm going to draw that. 1 is when I put the pen down, so if I lifted it up, you just have this dot here. And then 2, 3, 4, 5. Oh, I missed your question. I'm sorry. If there wasn't an H, would we need to write it in? No, you don't need to write any H's in the line angle formula. I'm assuming that you're talking about line angle formulas. If I missed your question and it was something else, let me know. Now, really important, since there are 5 carbons, I should have 5 points. And if it helps you to put these little dots, then go ahead and do it. But one of the most common things to do when you're starting this out is that you accidentally omit a carbon, or you add 1 carbon too many. So you might think, oh, the first thing doesn't count, so I'm going to go 1, 2, 3, 4, 5, and then you have too much. So be mindful of that. Make sure that you have enough vertices, which include the endpoints, to match the number of carbons in your structure. Now on the second carbon, which was this one right here, since I can't actually write up there, it's on a different window, I have a CH3 coming off of that, so I'm going to draw that. And so there you go. Oops. And then if I wanted to neaten that up without dots, that would look like this. There you go. So that would be CH3, CH3. So that's this one. This one is CH2. This one's CH2, and this one's CH3. Now, it takes practice to get used to this, but as you do this, you will start to understand what things represent in this notation. For example, endpoints like this are always CH3, and corners are always CH2. I'm not going to expect you to memorize that. That's something you're going to pick up as you go, okay? All right. Look, there's our answer. Surprise. In fact, while I'm thinking about that, let me fix that animation right now so that it... what slide are we on? There we go. Yeah, I just didn't include it in the animations. Appear. Now it should disappear. And I don't know what happened there. There we go. That's what I wanted to do. Okay, so I do have a comment on this. And that comment is, for any structures that I have drawn after revising my slides. So I did all these slides like 4 years ago, and it's still the same knowledge. When I went back over these and was redoing certain stuff, it's way, way easier for me to draw stuff using line angles as opposed to condensed structural formulas or expanded structural formulas. So you're going to see these structures a lot, and if you get confused, let me know, because I can draw all over the structures. I could do whatever I want to. I could do this. I could do that. And if this helps you, let me know. That's fine. Obviously, I'm not going to do this forever, but for the first chapter or so, I'm fine with giving you hints like that. Or even better, when you have the structures, if you have them on your paper, draw the sketch of the line angle structure, and then you draw over it. The more writing that you personally do, the more likely you are to remember this stuff later. Okay? All right. So I have drawn some squiggly lined things at the bottom. What the hell are these structures? I don't know. What I want you to do is turn those bottom structures into condensed structural formulas. And my hint is find the longest chain, because these look really complicated. So number the carbons. And then on the top there, I have a bunch of molecules that are either condensed structural formulas, or I just wrote hexane. What the heck is hexane? What do you think hex means? This is sort of me trying to prepare you for the next section, but if you don't know, feel free to just type hexane in Google and see if you understand why it's called that. Because when we start naming stuff in the next section, this will become obvious. Okay? So give this a shot. I'm going to give you like 2 or 3 minutes to try these, and we'll go over the answers together. Okay? See you in a bit. So 6 is correct for hexane. 6 what, though? When you're finished in the chat, let me know. I actually can't type in the chat at the moment because I have an issue with... I have like 7 Google accounts open right now, and it logged me in with the wrong one, and I can't log out without closing the chat, so I'm going to take care of that at the break. But I can't actually type in the chat right now, so give me just a second to fix that in the next like 20 minutes or so. But let me know when you're finished. Yeah, the prefix hex is short for hexa, like hexagon, which is the 6-sided shape. You're going to see these number prefixes come up quite a bit. So like pentane is pentagon, so pentane would have 5. And then hepta would be 7. Oh, sorry, the drawings down at the bottom are not the same as the things. So those are 2 different problems. So these... I could just draw a line here. So I want you to draw those 3 line angle structures, and then for these 2 down here, do condensed structures. So they're totally different problems. Yeah, I apologize. Whenever I put like a delineated line, each line is a separate problem, and they're never really related to other things on the screen, but always ask if you're confused, because I do realize that it is open to some interpretation. F is actually 2. Meth is 1. That's actually, I think, the next slide that we're going to talk about is those numbers. So, methamphetamine is amphetamine with a methyl group. So you're really close. We're actually going to look at the structure of methamphetamine at some point. Organic chemistry is basically how to make drugs 101. And then the bottom, those are, so the down there, the CH3 groups are methyl groups, and then the C2CH or CH2 CH3 groups are ethyl. So you're starting to get the idea. You're starting to put all these things together, which is great. And I know that a lot of people have sort of heard these things before. It's like, oh, I've heard of that. Yeah, I've heard of methamphetamine. What does meth mean? And it's CH3. That's what it is. That's a methyl. Well, so THC is, I think it's tetrahydro or it's tetrahydrotetrahydroxycannabinol. I don't actually know how many carbons that has, but you can look at the structures now because you would actually be able to read these line structures, and they show them like that. And I mean, let's not beat around the bush. Like, the whole point of organic chemistry is drugs, right? Like, these are, and when I say drugs, I mean literally everything. So food, pain medication, cancer treatments, even like opiates and narcotics and and weed and heroin and all that. Like, they're all drugs. Like, they all have an organic formula. And so to exclude one of those things is really kind of disingenuous. So we're going to speak openly and freely about any organic compound in this class and treat it as interesting with regards to its structure. Now, I'm not going to speak to like, oh, everybody should try heroin. Like, that's a terrible position to take. But as far as like what's the chemical structure of heroin and maybe why is it so addictive? Like, those are really interesting questions that hopefully we'll get to explore. I absolutely don't beat around the bush. Like, I am a very formal and open-minded sort of person. Um I actually when I was taking organic chemistry in yeah, I thought THC would be a lot larger of a molecule than 4 carbons. Cuz if it's psychoactive, it's probably either really really big or really really small. Um and there's reasons we'll talk about that when we get to enzymes. Um but when I was taking chemistry, so there's this version of the class which is for students like you who are in the nursing program. You don't need tons of OChem. You just need a general like overview survey class, which is what we're doing here. And then there's for biologists and chemists and engineers who are actually going in. Their job will be to make these molecules, so they need to know all these reactions that we're going to talk about next chapter. Um, and so you people like me, I got a whole year of this. And the third quarter of it was basically, here is a molecule, tell me how to make it. And some of those molecules were drugs. And I had an instructor who was very obviously a hippie. His last name was Dutch, and I think he came in wearing like a t-shirt and a tie all the time because he was just so laid back. And one of our homework assignments was literally, here is every street drug I am aware of, make it. Like, show me how to make it using the reactions we've learned in this class. And I wish I still had a copy of that assignment somewhere because it was just amazing. Like, here's mescaline. Show you can synthesize this from this starting compound. And so, yes, I know how to make all these compounds, or at least I knew at one point, and I could easily figure it out. Am I going to tell you the specifics? I mean, maybe if we get to it, but it's sort of beyond the scope of this class because we don't do those reactions. Like, I'm going to show you some reactions that we will do, but there are so many more. And to teach you, like, oh, how do I get the amphetamine in Sudafed to become methamphetamine? Like, that's actually a lot harder than it looks. And we don't actually cover that reaction just because it's not super clear for me how to teach it to you in the context of this class. So we're not going to be busting up methyllithium or something like that because we're just not going to do those reactions. We are going to do some reactions. And I apologize if I've talked through all this. Hopefully everybody's done. We're going to go to the sample problem preview. This is all public, by the way. Like, this is all on YouTube. So hopefully no stranger is out there going like, oh my goodness, who is this drug overlord peddling shit to his students? I'm like, honestly, this is just chemistry. This is what chemistry is. And one of the most important applications is medicine. So I could just as honestly teach you how to synthesize aspirin as I could methamphetamine. And from an ethical perspective, to me, those are the same thing. Like, I am describing to you how a molecule reacts to form another molecule. Now, from a practical perspective, one of those is much more dangerous. So we'll respect that. All right. So I asked you to look up hexane if you weren't sure what hex meant in hexane. We're going to learn it on the next slide. Something with hex in it has 6 carbons, and since this is just regular old hexane, you could just draw any 6 carbon chain that you want. This is probably the easiest one. We'll number the carbons just to illustrate. Now, if you had drawn this instead, that's also a hexane, or you could do this. Oops, I gotta actually connect them. Or, I don't know, whatever. You could do all sorts of things for hexane. Later on, we're going to talk about how do you differentiate between something that is linear and something that is branched. We're going to give a name to it. Oh, I got to select all or else it won't let me draw in there. All H. There we go. All right, CH3C, CH32, CH2, CH2, CH3. Okay, so looking at that structure, I see 1, 2, 3, 4, 5 carbons in a row, not counting any branches, because the branched carbons would be in parentheses. So I'm going to go, I'm going to do my 5 carbons in a row. 1, 2, 3, 4, 5. And then off of the second one, I have CH3 parentheses 2. So I have 2 CH3 groups. So it should look something like that. Now, if it helps you to, like, scribe notes out, you should totally do it. And so you could say, well, CH3, C, CH2, CH2, CH3. And you can just check those off of your molecule, just to be sure. Whatever it takes to get you to the answer, right? I'm sort of throwing a bunch of strategies out here at you. And then when you get proficient enough at this, you could just go do, and whatever. How many carbons are in this? I've got 1, 2, 3. Those next two are in parentheses. 4, 5, 6, 7. So I'm going to draw 7. 1, 2, 3, 4, 5, 6, 7. And then on the third one, I have a CH2 connected to a CH3, but the whole thing is in parentheses, so I'm going to just make it one group. And so let's label that for everybody. So there's CH3, CH2, CH, and then this right here would be my parentheses, CH2, CH3. CH2, 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 CH3. Do we have to draw it the way you showed us? Have we talked about conformations yet? I'm trying to remember. There's so much in this chapter that I'm just like, it all blends together. Yeah. So let me go over those questions one at a time. Let me clear what I've written in blue here, because there's some good questions coming up, and I want to make sure that I address this. Because we have to make the molecule as shown in some capacity. So I drew this, but let's suppose that instead you start zigzagging down like this. 1, 2, 3, 4, 5, 6, that's fine. Then my third carbon, you can go whichever direction you want to. Or maybe I went like this instead. That would be okay. Or in this one, maybe you just 1, 2, 3, 4, 5, 6. Oh, these all have 7. Sorry. Shit. Let's fix that. And then the third carbon, you went up for some reason. Like these are all okay. But what's important is that with the CH2, CH3 in parentheses in our condensed formula, we have to include this as a single group, which means that you do have to include it like this. And you couldn't say do this instead, because this would be CH3. This would be this. Okay? So be very careful that you are drawing what is being asked of you. Okay? It's real easy to make mistakes. All right, we're going to uncover these. Well, so a single point. So if this is my chain and I go like this, boop, and that's it, then yeah, that's a CH3. So end points are CH3. Be careful about when you say single line, because if I draw this as a single line, each of those ends is actually a CH3. So this would actually be this molecule. Okay. I think you know what you're describing, but the language that you're using to describe it could be misinterpreted. So just be careful. I ran out of space. Let me expand the canvas real quick. Image. Canvas size. Percent. So I want to make this 3 times bigger. Give me a second. I have to paint this layer. There we go. So I'm not drawing on transparent, and then you can't see it. Okay, so... Oh, that's not what I wanted. That looks kind of cool, but that's not what I wanted. There we go. Okay, so now what we're going to do is we're going to turn the molecules that you can see above here into structural formulas. How the heck do we do that? So I'm going to work from left to right. We're going to interpret what we see. So the first thing on the far left is a CH3. And so we're going to take this guy and do that. Then I have a CH2 next to that. Then I have a junction. I have a C, and I have 3 things connected to it. So one of them must be an H, and then the other one must be the CH3. Actually, you know what? Hold on. So this is correct so far, but it's probably just easier to write on this so that you can see what I'm doing. I'm trying to go between 2 windows, and so let me just do that again. Okay, that's the wrong pen. So this is what I had labeled so far. Okay, and we're just going to go left to right across the chain. This is the longest chain. 1, 2, 3, 4, 5, 6, 7, 8. All right, so carbon number 4, this would be CH. And it's connected to CH2, CH3 down here. And then carbon number 5 is CH. That's connected to this CH3 up here. And then this is CH2, this is CH2, this is CH3. We can just round it out. There you go. Oh, it did appear. Okay. I just couldn't see one of the lines of text there. All right. I don't want to erase that, so I'm going to get a new color. And we'll go over here. For this one, again, find the longest chain. So let's try and find that. So if I go 1, 2, that should be a 2, 3, 4, 5, right across the middle, you might be like, well, maybe there's something longer. And there certainly is. So 1, 2, 3, 4, 5, 6, 7, 8. That's a longer chain. So 8 is much longer than 5. Is there one that's longer than this? And the answer is no, because we've gone along the longest possible paths. The whole trick to this problem is really just it's deceptively drawn. And a lot of molecules are going to be deceptively drawn, so be careful, okay? So carbon number 1 is CH3. Carbon number 2 is CH2. Carbon number 3 is CH with a CH3 next to it. Carbon number 4 is CH2. Carbon number 5 has 4 things already connected to it. It's just C. But connected to it, I've got one methyl group, or sorry, one CH3 group and 2 CH3 groups. So we'll write that. Carbon number 6 is CH2. Carbon number 7 is CH2. And of course, I ran off the damn paper again. There we go. Now, this is a skill that you'll want to develop as you go. And it's challenging. So make sure you are doing the worksheet problems and getting into the hang of how to convert between these structures. Okay? Because I do ask you questions about this on the quiz. Like, which of these is this structure? Or whatever. All right, I believe that's the end of that section, and we're at the top of the hour, so we're going to go over to here. We're going to take our break. Let me get the timer on the screen here. And let me get the music back out. Where is it? There we go. So we'll start the timer. I will see you all in 10 minutes for more of this. Back in a bit. Oh, I need to reset the chat, so I'll let people know when I'm back in the chat, so give me a second. I tried. I can't hit the button fast enough. Alright, let's wind this down. Let's see here. So this should be working again. Okay, good. I had the wrong account logged in, and I didn't want to, like, type in the chat and then have to delete my comment. It was my streamer profile, and we don't want that. We don't want that on there. All my students watching me play Zelda. Alright. In this section, we're going to learn how to name things. This is going to be probably the least liked part of the class is naming. Maybe not, maybe reactions, but naming is something that we do have to do. We can't just draw pictures of everything, because those pictures take up space, and you also can't say, get me some picture, carbon, carbon, hydrogen, carbon, like, there's no easy way to say a picture other than giving it a name. So, the first thing we're going to name, we're going to name the shortest alkanes. We're going to name the first 4 with these names because that's just what we've chosen. These do not correspond to a number like hexane and pentane and etc. do. Beyond, we have just sort of established this as our truth. So, for instance, we have methane, where meth means 1 carbon. We've got ethane, where eth means 2 carbons. Propane is 3 carbons, and then butane is 4. So propyl and butyl will be 3 and 4. You're going to see that later on. Now, the name type that we described here is what's called a common name. And these are so common that we've accepted them as the nomenclature standard. Now, there's no way around these. You have to commit these to memory. By the end of the quarter, if you don't know what methane is, or ethane, just off the top of your head, then you really have not been paying attention to anything, because we're going to use those so much. Propane and butane, not as much, because as they get bigger, it gets harder to make them as a side chain. And yeah, if you watch King of the Hill, exactly, you know all about propane and propane accessories, so. Alright, so those are the first 4 alkanes. After that, we start giving them number designations for the number of carbons. So pentane has the penta for its prefix, and penta means 5. Hexa means 6. Hepta is 7, and so on and so forth. I'm kind of sloppy here with the pen, but... And this goes all the way up to 12. So 11 is undeca, U-N-D-E-C-A. And then 12 is dodeca. Now, there are prefixes past 13, but what tends to happen at that point is they just write the number and then dash and then ane. So a carbon chain with 14 carbons would be a 14-ane. We're not going to go past 10 in this class as far as naming. If something is longer than 10, I will just truncate it down to 10. Okay. Now, this is in table 12.3 of your text online. But these are worth committing to memory, too. Because what these are going to be our chain backbones when we name stuff. All right. So now what we're going to do... Oh, first I'm going to have you do some practice problems. So I want you to draw the structural formula for the compound with 9 carbons, so then give it a name on your paper. Actually, no, we don't need to do this right now. You could do this for practice, because this is very straightforward. Because if I was to draw the line structure for this, okay, it's got 9 carbons, so here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. There you go. And then what is 9? Well, that's nona. So this would be no name. If you're riding on the horse with no name, that's very different. That's a very different song. I kind of forgot the lyrics, but I know horse with no name at least. So, all right. Now what we're going to do is we're going to start giving names to all of our molecules based on how many carbons are in their longest chain. And then the branches that we see... Yeah, most people don't get that reference. It's okay. I'm an 80s kid, so that's why all of the Paradise Killer music that I'm playing is like, wow, the 80s were this strange and magical place. Like, this is basically 80s and late 70s music that I'm playing, which is probably why I like that game so much. Like, it's just... the music is amazing. We're going to name these molecules based on the longest chain. So, first I'm going to put up these names on the board here. And I'm going to put a note right here on this, that this is a common name. Born in 99. You're so young. So, don't worry about the name isobutane here. So, right here, this statement right here is kind of misleading because this is for a common name. Okay? What we do care about, though, on this slide is that specifically, if you see N or iso, the term N means that the molecule is quote-unquote normal. What a normal molecule is it's linear. Or in other words, there are no branches. Whenever you see iso, you should think, oh, iso means that it's branched in some way. But that's really all you can tell about it. So, iso is kind of unclear. And so it ends up becoming a common name. If I have isobutane, I have a methyl group connected in the middle of a propane chain. That's just what isobutane is. Now, if you remember what those two things together, then that's great. But there's really no systematic way that links those two things together. So this is kind of a common name that doesn't help us in the long term. And so common names are not super helpful. You're going to see them, but you're not going to be able to apply a common name to everything. So what we need is a consistent way to name stuff. And so whenever we have lots of branches, common names fall apart. So we need to figure out how to name these molecules, because these are all hexanes. But are they all isohexane? No. I mean, the branches come at different spots. So we can't use iso for everything. Iso is going to show up in very specific common names. So what do? Here's what we do. We're going to go back and name all those things, but I'm going to use a different molecule for our example. So what we're going to do to name a molecule is that we're going to identify any groups that hang off of our main chain. Remember that the main chain is the chain that's the longest. Okay? Now in this case, that would be this right here. Let's highlight it in yellow. And so I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons in this chain. So this is my main chain right here. And what that means is that anything else that is not on the main chain becomes a group. So I'm going to highlight those in blue. So these right here are called groups. Now, before we move on, what I want to do is I want to identify some of these groups. So let me put this up here so you can see the chain. Oops. I got to click on this little dot. There we go. And what we're going to do is we're going to identify groups. Okay. There are a lot of groups, but here are the ones that we are going to see most often in this class. So what I'm going to do is I'm going to use a squiggly line to represent, which you can't see because I just went off the screen here. So this squiggly line is the rest of the chain. So this is the main chain. We'll just put main chain. Okay. And so if I have something like this, we're going to call this group what it looks like. It looks kind of like methane hanging out, except we're going to put ul at the end. So this is a methyl group. And we'll just keep this chain going down. This looks like a 2-carbon chain, so that would be an ethyl group, because it looks like ethane. And I can just keep doing this as long as I want to. This looks like propane, so we'll call it a propyl group. And this looks like butane because there's 4 carbons, so this would be a butyl group. Now, if I was going to draw these as pictures, this would look like this. So here's my main chain, and then somewhere off that is a single carbon. Here's my main chain. Somewhere off that is 2 carbons. 1, 2, 3. 1, 2, 3, 4. So you're going to see these groups all the time. Now, if you're looking at the little diagram above, you can see the methyl groups right away. But if you're looking at that group on the right, you're probably thinking, well, it kind of looks like a propyl, but isn't it connected to the wrong thing? And that's absolutely correct. There are more groups, so we're going to keep going. And so if I have a carbon that's like this, CH, CH3, 2, this is what's called isopropyl. Because remember how iso means it branches somewhere? I have a branching propyl group. Or in other words, if this is my chain, here's my branch group. Isopropyl basically looks like a Y sticking off of the main chain. Now, there are other groups for butyl too, and I'll include those here as well. So we have CH, CH3. Oops. I wrote the wrong thing, sorry. CH3, CH2, CH3. And so what this is called secondary butyl. And what that looks like is squiggly line. I've got my CH3 and then CH2, CH3. So this is sec butyl. And then the last one that we can have is called tertiary butyl or tert butyl. Which looks like this. Yeah, so the iso for our groups is only ever going to come up with isopropyl. It doesn't come up with the butyls because there are multiple ways to do it. Now, if you're looking at these and going, what the heck? Like, where are these going to come up? Really, what I'm just trying to get you to do is memorize that there is a specific branching or pattern to carbons and then associate a name with it. So for our purposes, this is what we're going to need for this practice problem coming up, is because you see that directly above. It's right there, right? So we're going to use these names of these groups in naming our molecules, okay? And then later on, we're going to add more groups. That's going to be a section that we do at the very end of the chapter today. Not today, but later on. All right. So we've found the longest chain and we've identified the groups here. And you'll notice that I have numbered the longest chain like this kind of arbitrarily. We'll talk about numbering in a second. It turns out I wanted to number it this way specifically for this problem, but we're going to talk about why I numbered from right to left and not left to right in just a second, because there is a direction that you're supposed to go based on your molecule, and you'll see what that means in a second. Okay, so first of all, there are 9 carbons. That means that when I give this a name, it's going to have nonane in its name. The next thing that I want to do is I want to take the number and the group and put those together. So this, let's start with an easy group. So this one is at position 7. This is a methyl group. And it's a position 7. So I'm going to go 7 hyphen methyl. Same thing right here. This is a methyl at position 6. 6 methyl. Do you remember what this group was called? Hopefully you just said isopropyl, and it's at position 3. I have now numbered the positions of my groups, and what I'm going to do is I'm going to organize them in my name alphabetically. How do I do alphabetical? Well, let's see here. So I got methyl, which starts with an M, and I've got iso, which starts with an I, so I'm going to start with I, because I starts before M. And then I'm just going to name them left to right. Well, sorry, not left to right. I'm going to name them in alphabetical order, so I'm just going to go through all the groups here. So 3-isopropyl. I have a methyl at 6 and 7, so I'm going to put both numbers. I'm going to separate them with a comma. And because there are 2 methyls, I'm going to put di to indicate that there are 2 methyls. I thought I'd have enough space for this, but I don't. And there's the name of it. 3-isopropyl 6,7-dimethylnonane. So what I'm going to do, so I'm going to get rid of these highlights really carefully. Oh, that's not what I wanted to get rid of. There you go. And then we're gonna talk about what we just did, because that's a lot. Okay, so here's this group. Here are my methyl groups. That's this part. And then the longest chain was a nonane. That's this part. Okay. All right. So I've already showed you what the groups look like on the previous slide. So there are our groups. How do we label our groups? We put the numbers of the positions, and then we list the groups alphabetically. If there are more than one group, we're going to put a prefix in there to represent that. So if there were 3, it would be trimethyl. If there were 4, it'd be tetramethyl, etc. And then finally, it's a nonane, so we're going to add that too. All right. I'm basically throwing you in the deep end with this, but that's sort of what we have to do, because if I give you simple molecules, then you see these and you'll go crazy. And in reality, we work with these more complex molecules. I don't know what this one specifically does, but... So now that we know this example, let's go back several slides. Oops, that's forward. I hit the wrong button. And start naming these. So we're going to do the same thing. We're going to show that they all have different names. So first, find the longest chain. There it is. There are 1, 2, 3, 4, 5 carbons. So this is going to be a pentane. I'm going to number it in the correct direction for now. We'll talk about why I'm numbering it this way later on. What group is here and what position? So what should I tack on front of pentane? And hopefully what you decided was that. And there shouldn't be a space there. That should be all one word. 2-methylpentane. What would this one be called? What do you think? I'm going to number the chain again. And then I'm going to put this one on here. And I'm going to number the chain again. And I'll let you stew over that for just a second before I put the answers up. What would the names of both of those things be? Now that we've done the complex example, the simple one feels really easy, right? So because that methyl is at position 3, this is 3-methyl pentane. This one has a methyl and another methyl at position 2, but this is only a butane because there are only 4 carbons. So both of them are at the same position, so we just write the same number twice. 2,2 dimethyl butane. There you go, you got it. So make sure you use di, D-I, instead of bi. Bi actually means half. Like when you bisect something, you cut it in half. Yeah, when you dissect something, you cut it into 2. Although it seems like the same thing. That sounds like semantics, but that's just what we use for science. Because you would also think, oh, well, what about bicycle? Yeah, it has 2 wheels, but that's a common name. In sciences, whenever we apply bi to something, generally what that means is that there's something with a ratio of half in there, whereas di has a ratio of 2. All right, so now what we're going to do, let me go back to the slide that we were on here. So what we just did, this awful thing that we just did, this is called IUPAC nomenclature. IUPAC nomenclature follows a very, very specific set of rules, and the rules need to be committed to memory, or else you're just going to be looking these up every time, and that's going to be frustrating. So let's go over these rules. The first rule is pretty straightforward. We've probably got that one memorized already. Find the longest chain, name it, but don't number it yet. I don't actually know enough Greek or Latin to really answer that, honestly. But you might be right. One of them might be Greek and one of them might be Latin, and I don't know which one is which. All right. Step 2, you are going to number the carbons along the chain if it is branched, but there's something that isn't written here because it comes up later. I'm going to write it here for you. Number them, there we go. Number them such that the lowest number occurs at each branch. I'm going to put in parentheses, starting with first. Because if I number them in a reverse direction, I might get a different number. So for example, let's suppose that I have this. And I have a methyl coming off of it. If I number it this way, the branch occurs at position 2. But if I number it the other direction, it occurs at position 3. Which would mean that 2-methyl butane and 3-methyl butane would be the same thing? That doesn't make any sense, right? Why would I have 2 names for the same thing? So, we're going to number them such that the lowest number occurs at each branch. Now, if you have multiple branches, which you will, you want the lowest possible number sequentially. So the first number should be the lowest. If there's a tie in both ways, you can start with 1, for example, then the second number should be the lowest. And whenever you have a choice between 2 different numbering schemes, if I number them forward and backwards and I get this, 1, 2, 2, 4, 5, and then for this one I get 1, 2, 4, 4, 5, this would be the correct numbering scheme because in the third comparison, 2 is lower than 4. Clear as mud, I'm sure, right? The point is you want the lowest possible number. So count in one direction and count in the other direction, and look where your branches are, and however you get the lowest numbers, that's the correct numbering direction. Once you've numbered it the right way, locate and name any groups of the chain, and then do all the numbers. Put those numbers and the group names into your name and arrange the names alphabetically. Giant pain in the ass, I know. Naming stuff in OChem sucks. Remember back in the day when it was just like sodium perchlorate and disulfur tetroxide, like all that naming? Yeah, I miss those days. Not anymore. We have to name it this way now. All right. So these 4 steps, remember with the caveat for number 2, you want the lowest possible numbers, which you're going to see on the next few slides. It's going to come up. This is what we're going to do. In this order. Don't do it in any other order. You'll get the wrong answer. All right. Finally, if you have, when you've arranged your groups, you have more than one of the same group, add some prefixes to it that represent that. So di, tri, tetra, etc. If you have 2 methyls, 3 methyls, 4 methyls, or whatever. All right, so let's take all that and apply it to this molecule. So we need to number this molecule, and I'm going to put 2 numbering directions on the board here. And I want you to tell me which is the correct numbering scheme, red or blue? Based on what we just talked about, which direction gets you the branches at the lowest number? And blue is correct. Very good. So our branches occur at 2, 5, and 6, whereas on the red path they occur at 3, 4, and 7. So if I were to write those down, The first one breaks the situation wide open. 2 is less than 3, so we would pick it. So we're going to number with the blue path. Then what we're going to do is we're going to name the groups along the blue path. So this is 2-methyl. This is 5-ethyl. And then this is 6-methyl. I'm going to arrange them now alphabetically. Ethyl comes before methyl, so I'm going to put the ethyl group first. 5-ethyl. And then I have methyls. I have 2 of them. I'll list their numbers. And then di, because I have 2 of them. Methyl. And then what is the chain? It's an octane. 5-ethyl, 2,6-dimethyl, octane. And there you go. All right, let's do more examples here. Actually, you do these examples. So I want you to name the longest chain. Be careful. And then down to the bottom, I want you to draw pictures from these names. Drawing the pictures is actually a lot easier than turning a picture into a name. And we'll go over a strategy for that in a little bit. But for the start, what I want you to do is try it on your own and see where you get. Okay? Give this a shot, and we'll go over the answers in about 3 minutes. See you in a bit. That's close, but there's an issue. See if you can find it. It has to do with the end. Have I tricked you? Is it really an octane? Yeah, we gotta find the longest chain. And so I can hide it from you. And it's not difficult for me to hide the longest chain by just making it bend in some other direction. So be really careful. Number it all the way through several times until you're convinced that it's the longest one. Generally speaking, going down long branches is a good way, especially if those branches are towards the end, because then they're not branches. So the correct numbering scheme for this would be that. And then we got to name the group, so we got 2-methyl. We got 4-isopropyl. And then 7-methyl. And that looks like that's it. So let's arrange them alphabetically. So this would be 4-isopropyl, 2,7-dimethyl, decane. All right, going down here, draw a picture of these. I personally think that this is way easier to do. And the reason that I think it's easier to do is because once you've drawn the base chain, you're pretty much all set. So I hope we all wrote down those groups, because I have cleared them. But you can always go back in the video. All right, so this first molecule is a heptane. So I'm going to draw my heptane. 1, 2, 3, 4, 5, 6, 7. And then at position 3, 1, 2, 3, I have an ethyl, so I'll do that. And then at 2 and 6, 2, 3, 4, 5, 6, I have a methyl. There we go. 3-ethyl, 2,6-dimethyl heptane. That's easy. We can do that. How about this next one? 3-isopropyl, 2-methyl pentane. So pentane, we'll start with that. 3-isopropyl, 2-methyl. There you go. Now, interestingly, you might be thinking, well, wait, hold on. So we numbered it this way. What if instead I had done this? Well, interestingly enough, at position... Oops, that's not a 2, that's a 1. Interestingly enough, you still have a methyl at 2, and you still have an isopropyl at 3, if you number it this way. If you number it a different direction, then you don't have the lowest numbers possible at the first branch. So, oftentimes, a lot of these, it will work out the same way. Okay? It'll work out the same way, or you will violate some other rules, such as you want to have all the numbers be as low as possible when you compare each first initial branch, the second initial branch, etc. All right. If you have any questions on naming stuff, let me know. We're going to do more of that towards the end of this chapter, which we'll cover on Thursday. Sorry, not Thursday, Wednesday. Mixing up my classes. All right, but for now, let's talk about in the last 5 or 6 minutes of class or so, let's talk about some physical properties of alkanes. There's really only one thing. There's 2 things you need to know in this section. This is really a short section. And those things are alkanes are insoluble in water because they're nonpolar, and boiling point. We're going to talk about how boiling point works in a second here. All right, so any alkane that has up to 4 carbons is a gas. 5 to 20 are liquid, and past 20 are solid. So what that means is that if I write down a formula and I say, predict the state of this molecule, you would go, okay, it's an alkane because it follows the 2n plus 2 for hydrogen. And it's between 5 and 20, so this would be a liquid. Easy enough. Now, why does the boiling point increase as things get bigger? For example, alkanes with 4 or fewer carbons have a boiling point below room temperature. They're gases. 5 to 20 have a boiling point above room temperature, and it gets progressively higher and higher and higher the more carbons there are. And the reason for this is because of dispersion forces. Hydrocarbons contain only C's and H's. And as we said before, these types of bonds are all nonpolar. So no dipoles exist in alkanes. The only intermolecular forces that are possible in alkanes are dispersion. Dispersion forces being the uneven distribution of electrons. From that, if you remember 121, you might recall that dispersion forces come from electrons, and if you have a higher molar mass, you have more electrons, and when you have more electrons, you have more dispersion forces. So, as things get bigger and more electrons are present, you have more dispersion forces. What that means is that as the molar mass of these molecules increases as I add carbons, the dispersion forces between them get stronger, and they're held together more tightly. I need more energy to cause them to separate out and become a liquid and then a gas. So as molar mass increases, dispersion increases, and boiling point increases. So boiling point increases with the number of carbons. What else can we talk about? Let's talk about isomers. So I'm going to show you a bunch of isomers with their boiling points, and you're going to notice that the ones that are linear have higher boiling points than the ones that are branched. And the reason for this is because if I was to take these shapes and line them up next to each other, so if I put another like this, I have a lot of surface area for dispersion forces to occur. So dispersion forces occur along surface area. But if my surface area is reduced due to branching, so for example with this molecule, now I have less surface area because this branch gets in the way. Sure, I could flip the molecule around, but then the other sides would not be able to hydrogen bond with other things, and they would just be held on in a little pair here. And then same thing over here with this guy. Like, these kind of fit into each other, but not perfectly. And so the amount of surface area that I have between my molecules is reduced because of these different shapes. As a result, what happens is the more branches that you have, the lower the boiling point is. So let's write that down. more branches, lower boiling point. Now, the takeaway for that is I have to be using that concept for alkanes with the same formula. So these are all alkanes that have 8 carbons. If I compare something with 8 to something that's branched with 6, that's not a fair comparison because something with 8 just has more electrons. It should have a higher boiling point, regardless of how many branches either one doesn't have. Okay, so you're going to see comparisons like this. And what I mean by this is, like, wait a second, this is immediately what I told you I wasn't going to do. But is it? It's really not. Because if you look at this first one and the second one, you'll notice that they both have the same number of carbons. And then I have this one. So what you can do is you can place this first one and this third one into an order, and then use that to place the second one into an order. And I just realized that that's the answer down there. That didn't get animated properly either. So let me fix that real quick. All right, they should disappear. Oh, they didn't disappear. I got to do that. There we go. So let's look at these first. So who is the higher boiling point? Is it hexane or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? Decane. So this is hexane. And this is decane. And this is 2,2-dimethyl butane. So decane has the higher BP. This one has a lower BP. When I'm comparing these two together. Okay. Now let's look at this one. Let's compare 2,2-dimethylbutane with hexane. And what you should do when you make this comparison here is you should say, oh, well, this is more branched. So in this comparison, it has a lower boiling point, and this one has the higher boiling point of this pair. So once you've got that, now you can arrange them from lowest to highest. Of the blue pair, this one's the lowest, so we'll put it down there as the lowest. And then of the red pair, hexane has a lower boiling point than decane does. And let's see if that matches up, and it totally does. Look at that. Okay, so you're going to have these little comparison like situations that you're going to need to decide which one is highest and which one's lowest. And there will always be a logical way to do this. First, try and find the highest one or the lowest one based on what you know. So here, I was able to compare decane with the other ones, and I know decane's going to be the highest because the other two are hexanes. And then I can compare the hexanes to each other. You might have a problem that has maybe 4 of these. Like, maybe I could give you over here, I could also have thrown in butane just by itself. And you would immediately know that this would be the lowest. That's not how you spell lowest. I wrote off the screen anyway, you can't see it. You would immediately know that that one is the lowest because it only has 4 carbons. So, things like that. So, that's the sort of problem you're going to see on the quiz with regards to the boiling point. The last thing that we'll talk about before we go is that alkanes don't dissolve in water because water is polar and can hydrogen bond. So this is H2O. Water does a lot of hydrogen bonding. Up here, oil only has dispersion. And so because those two don't have similar forces, they don't dissolve in each other. You might remember from 121 when we talked about solubility very briefly, like dissolves like, and that you needed to have similar intermolecular forces in order to dissolve in each other. Water is so powerfully hydrogen bonding that it only hydrogen bonds with other things that can hydrogen bond. Since oil can't do that, water would rather interact with itself than oil, so the two separate out. All alkanes will separate from water. I think that's it. Yeah, this is just like what are alkanes used for? We use them for like waxes and stuff. So you're going to see that. And wax dissolves in alkanes. So if you were sealing like a bottle of gasoline, which is an alkane, with wax paper or something waxy, it would dissolve and melt, which would be no good. So don't do that. Okay? That's the end of the physical property section. So that's all we're going to do for that. We are all out of time for today. It is now 2 p.m., so I'm going to go over to this screen, get the outro music set up here, because we are all done for the day. I want to thank everybody for coming out to the lecture. If you have any questions, please let me know. Send me an email, drop a line in the Discord, whatever you need. There are people using the Discord now, and some questions are going up. So ask those questions whenever you need to. I will get to them when I can. Have a wonderful rest of your day, and I will see you tomorrow for another lecture. Have a good night.